Welcome back to My Favorite Universe. Today I want to talk about a subject that's on a lot of people's minds, a subject that has been worked into 2 feature-length Hollywood motion pictures. I'm talking about killer asteroids. Asteroids that are out there in space, normally minding their own business, and occasionally a wayward one comes our way and slams into the Earth. It turns out that if you look at the statistics of asteroid impacts, they represent the biggest threat to human civilization that exists in nature. The biggest threat because, well, most are small and cause little or no damage. The fact that there are few that can render the entire species extinct means we ought to be paying attention to these things. We know Earth has been slammed before by some combination of comets and asteroids because there's evidence in the fossil record. Paleontologists have known for a long time that there are periods in Earth's history where it was teeming with life, and then they hit some boundary in the sedimentary rock, and then most life is gone in the next layers. Before we had a deep understanding of impacts, it was often ascribed to, oh, there might have been too many volcanoes, or the climate change, or the ice age, or whatever. We now know every now and then Earth gets a deposit of energy sufficient enough to cause the damage observed in those layers. We know that in that fossil record, about every 100 million years, plus or minus a few, Earth loses anywhere between 50 to 90% of all the species on the planet. So it's more than just, well, there's life here and then no life on the layer that follows it. Maybe all the life migrated away from that spot. But you look all around the world, and the evidence is irrefutable and incontrovertible that when the life disappeared here, it also disappeared on another side of the Earth. Nobody was running from one place to another. Something happened catastrophically. So we're going to spend the next few minutes talking about what this risk is, and trying to get closer to it and come to an understanding of what the risk is and is there anything we can do about it, being intelligent human beings. The only intelligent species ever to walk the face of the Earth. And I'll define intelligence by the capacity to maybe build something that'll knock it out of the sky. Let's begin with a statistic. Perhaps you don't know, but the chances that your tombstone will read "killed by an asteroid" are the same as the chances of your tombstone reading "killed in a plane crash." You might say, well, how's that possible? You know of people, either firsthand or secondhand, who might have died in a plane crash. You don't know anyone, I'm sure, you don't know anyone who's been killed by an asteroid. And a couple hundred people a year die in airplane accidents. 0 die a year in asteroids. So what am I saying here? It's because you got to look at it at how it works. We'll go 100 million years, and then an asteroid large enough will strike the Earth and kill 10 billion people. So that's 100 million years, 10 billion people. So now let's talk about airplanes. Airplanes, on average, might kill 100 people a year. But if it does that for 100 million years, at the end of that same baseline of time, airplanes have killed 10 billion people. That's why those 2 data are equivalent. The risk of death are the same in an airplane as they are by asteroid. Now, this is something we should worry about. It's something we need to alert the legislature about. The problem is, of course, to go to someone who needs to get reelected every 2 years, that something might hit in the next 100 million, it doesn't square with the attention span of Congress. But I'd like to believe that in the next few minutes together, I can convince you of why it's an important step to take. Let's look back at what started all this. That's the early formation of the solar system. We started out as a large gas cloud. with the right mass to make one star in its center, the sun. The rest of the material enriched with heavy elements, elements beyond hydrogen and helium, the kinds of elements that make planets, that's there mixed with whatever hydrogen and helium did not participate in the formation of the star. So we have gas coalescing, making molecules, molecules making dust, dust making rocks, also volatile dust making ices. So you get rocky debris, you get icy debris, depending on the distance from the sun where it formed. If it's too close, you're not going to condense out the ice. So most of our comets reside very far from the sun, for example. So there's all this debris. Now, some debris is a little bigger than the others, so that will have a little extra gravity, a little bigger cross-section to impact, and so they'll grow by accreting more of the debris. And through this method, you can actually build and create large masses out of what was previously just this scatterbox of small objects in orbit around the host star. So by these collisions, small objects become large. Slightly bigger ones grow bigger faster than slightly smaller ones. They reach a large enough size, gravity then shapes them into a sphere. We spent a whole lecture on that, on being round. This ensemble of spheres is what we now describe as our solar system, the planets and the planets' moons. But not everything ended up part of the planets. There's still a lot of debris out there. In fact, even after you form the planets, there's a period of sort of cleanup after the initial formation. There was 600 million years where planets, fully formed, were still hit. Technically, they were accreting, but they no longer were growing appreciably in their total mass. They were simply being subjected to impacts. In this 600 million year period, we call it the period of heavy bombardment. Impacts came at such a rate that there wasn't time for the surface to cool down between this impact and the next one. So the average temperature of the surface remained high. High enough to kill anything that might have formed. High enough to break apart complex molecules. High enough to consider the surface of the Earth a sterile environment. In fact, the moon, if you look at it, for an orb that size in the solar system, it ought to have much more iron in it than it does. We look at the moon. The moon has very little amounts of iron. We say, why is that so? Latest models show that the moon was spawned, was hewn out of the surface of the Earth, that a Mars-sized impactor had a glancing blow onto Earth's crust, grabbing whole pieces of the Earth and thrusting it back out into space, coalescing again, forming a sphere in orbit around the Earth, making today what we call the moon. Since the Earth had already segregated its materials, with iron being towards the center and the lighter rocks towards the surface, it makes sense then that you'd make an entire orb just of rocky material with very little iron, because the iron had already been filtered out, so to speak. So now think about that. When did life begin? The earliest records of life fossils on Earth go back about 3.8 billion years. So if you say that's the earliest fossils, and how old is Earth? Earth is 4.6 billion years. Subtract those two numbers, you get 800 million years. You say, all right, it took life on Earth 800 million years to start. That's a commonly quoted number. But don't requote that number, because that's not fair to the fertility of organic chemistry. You know why? Because you can't include the 600 million years that we were sterile. Nothing could have formed. That's just not fair. Wait for that to die down a bit, so that at least between impacts, the Earth had a chance to cool and make complex molecules. And so, in fact, 4.6 billion minus 600 million, that takes you right back to 4 billion years. Start your life clock at 4 billion years ago. You say, wait around, where's life? You wait 200 million years, there's your one-celled creature. So life was remarkably fertile. The early ingredients. And what were those ingredients? Carbon, nitrogen, oxygen, silicon. The ingredients of life. Many of which were brought to the surface of the Earth by those impacts. Water brought to the surface by comets. So this period of heavy bombardment, in fact, was kind of like soup starter for life in the early Earth. Now, we continue to accrete, but not at that rate. And that accretion, that's the official word, accretion. I actually don't like that word, but it's the official term. People more formally use the word accretion when they really should talk about species-killing, ecosystem-destroying impact, because that's what these things are. That's what they, and it's the leftovers of the solar system. They're still out there. It's just that the impact rate has dropped into what we might consider a manageable rate. If there's enough time between really bad impacts to evolve species from one form to another. So in that respect, it's okay. It's okay. But what is that leftover? What are the leftovers? Well, first we have tens of thousands of asteroids in an asteroid belt. That's a region of the solar system in orbit around the sun between Mars and Jupiter. We have trillions of comets. Trillions of comets. Some are nearby, like Comet Halley, has only a 76-year period. Other comets go very far away and have orbital periods of thousands of years and tens of thousands of years. But if you add them all up, it's trillions. Since these are left over from the early solar system, if you capture one or experiment on one or get a piece of one, they're kind of like fossils of the formation of the solar system. Fossils. And so anytime you see someone trying to send a mission to a comet, pay attention to that, because these comets have been hanging out there for billions of years, untouched, unscathed, unaltered. Now, I don't know about you, but every time I drink a cup of water, I think about comets as the delivery system for this refreshment. It keeps me connected to the cosmos. Now, most comets do not cross Earth's orbit. Most asteroids don't cross Earth's orbit. We don't have to worry about those because the dynamics of the system prevent them from essentially ever crossing Earth's orbit. But there are samples of comets and samples of asteroids that do cross Earth's orbit. Those are the ones we're worried about. And they cross every time they come around. They say, well, why don't they hit us if they cross our orbit? Why don't they hit us? Well, you've crossed the street before, the same street that trucks have gone by, and you didn't have an encounter with the truck because you crossed at different times. So these are very big orbits. A lot of real estate out there. So you can go a long time without ever actually colliding. You're at the right place at the right time rather than the wrong place at the wrong time. So what we want to do is actually sort of catalog the bad ones. In fact, let's look at a real asteroid. I've got one, asteroid Eros. Look at that. That's a potato-looking thing, if I've ever seen one. Funny-looking potato. That's a real asteroid called Eros. That would do serious damage if it hit the Earth. In fact, every now and then we see one of these come by in a close approach. Close approach might be between Earth and the orbit of the Moon. Even if not that, suppose it's twice the orbit of the Moon. That's close. People call it a near miss. I call it a near hit. It didn't nearly miss us. It nearly hit us. If it nearly missed us, it would have hit us. I think of them as shots across our bow. We see them when it's too late to do anything about it, either coming towards us or receding from us. We've got to watch out. In fact, a few years ago, there's an asteroid whose orbit we calculated to intersect with Earth sometime in the next 100 years. And the original calculation gave a high probability of that, and everyone went berserk. When I say everyone, I mean the media went berserk. Every astronomer in every town was shoved in front of a TV camera saying, is this bad? What's it going to do? All astronomers became the most important people in the world for 48 hours. And what happened? Better data became available in that short amount of time. We recalculated the orbit and found out, no, it's not going to collide with Earth. But it wasn't before the press gave it enormous levels of attention. And my favorite headline of them all was from the New York Post the day after the calculation was refined. And instead of saying the asteroid almost hit us, but it's not anymore, what headline did they give us? Kiss your asteroid goodbye. I thought that was a brilliant headline in the style that only the New York Post can put together. And I remain astonished by the auxiliary headlines that go together with these major other headlines. Kiss your asteroid goodbye. This is an article about what might have been the end of all civilization, and it's combined with a movie review of Leonardo DiCaprio's recent film. So this is the world in which we live. Do we need evidence that we've been hit other than extinction layers? We've got evidence. You ever been to Arizona? Arizona's known for its holes in the ground. The one most people talk about is, of course, the Grand Canyon, but the one I think about most is a big crater, Meteor Crater, Arizona. Before it was called Meteor Crater, it was called Barringer Crater because people didn't know that it was made by a meteor. It took the efforts of the geologist Eugene Shoemaker, who, as part of his PhD thesis, analyzed the structures of the crater, the surrounding areas, and he was kind of like a planetary geologist. He knew about craters on the moon and what could cause them, and postulated that, in fact, this was made by an impact, as opposed to what was previously believed, it being a volcanic caldera, even though there's no evidence of volcanic activity anywhere for hundreds of miles from that location in Arizona. So that crater, one of the most famous on Earth because of how well preserved it is. It's not heavily eroded. You don't keep your crater shapes for very long on Earth because of the weather and the elements are devastating to surface features. So here we have a crater. You want to get a sense of how big this is. If you played a football game in the center of that crater, there's enough seating for 2 million people around the crater edge. My first visit to Arizona, I took a trip to the Grand Canyon, and I was underwhelmed by it. Yeah, it was a big hole in the ground, but it took however long nature took to make it. I don't know, millions of years, whatever. Went to Meteor Crater, came up to it, that impressed me. Because I said, look at this hole in the ground, and how long did it take to make? 1/10 of a second. I remain impressed with the power of nature simply by my memory of visiting that crater. And by the way, this is a sample. This is a piece of the larger meteorite that made that crater. It's an iron-nickel meteorite, 90% iron, 10% nickel. It's very heavy, very dense. It's hard to convince you of that out there in video land, but I can put it on the table, and you get a sense of that just from the sound. Now, the most celebrated extinction event in history is when the dinosaurs kicked. Well, when was that? Well, we call that the Cretaceous Tertiary boundary, the KT boundary, which is a boundary in the rocks that tells you, that sets up a difference between what happened before it and what happened after. We've always known about that boundary, but no one really knew what caused it. Was that event as significant as Meteor Crater in Arizona? Meteor Crater in Arizona, in fact, is small. It would have wreaked havoc in its local area 50,000 years ago when it hit. But beyond that, it's a minor encounter with an asteroid. If we're going to blame an asteroid for the KT boundary, it's going to have to be something bigger than that. And the paleontologists were in denial. Well, if you're a paleontologist, what do? You look for fossils, so you're looking on the ground. They never looked up. They looked for solutions to their problems on the ground. Astronomers looked up. Hey guys, we've got stuff coming. I can deliver you significant sources of energy that can take out your dinosaurs at about the rate that all your fossil records are going away. It wasn't until recently where that community finally warmed up to this fact. So let's take a look at an artist's rendering of what this might have been. The KT boundary, as I said, 70% of all Earth species, land species, went extinct. No animal bigger than a bread box survived. Evidence indicates that the impactor was about anywhere between 10 and 20 miles in diameter. It came in and hit the tip of the Yucatan Peninsula. It's known as the Chicxulub crater. There's a crater there. We found a crater. It's the smoking gun. After hypothesizing an asteroid took out the dinosaurs, we found a crater of about the right size, and we dated the crater 65 million years ago. Something bad happened on Earth 65 million years ago. Oh, by the way, the dinosaurs went extinct. Let's get another view. Here goes one, shows some pterodactyls flying by. This one hits the ocean in this image. Either case, you're hosed. Just don't try to pick your spot. It won't matter. You're dead. I like to think of T-Rex observing this, and then, of course, what's the next scene we have of T-Rex? Of course, he's all bones in a museum. Makes you wonder, though, can we have our cake and eat it too? Can we say, oh, these impacts are bad? Well, I don't like these impacts. They'll kill us. Well, wait a minute. Our ancestors, our mammalian ancestors, tree shrews running underfoot at the KT boundary, survived that impact. They spent their whole lives not wanting to be eaten by T-Rex. T-Rex gets knocked off. They now have a fresh ecosystem in which to populate. Modern-day mammals owe their origin, or the origin of their diversity, and they're spreading across the world by the virtue of the dinosaurs having been taken out of the picture. We can't simultaneously be happy that we live on a planet, be happy that our planet is chemically rich, brought to us by impacts, happy that we're not dinosaurs, but yet somehow resent the possibility of it being of us being knocked out by a planet-wide catastrophe, because a planet-wide catastrophe enabled us to be here in the first place. So maybe we should just take it in stride. What kind of collisions can you have? Well, think about it. If this fell from 12 inches above my head to hit my head, it would probably crack my skull. Now imagine this going 45,000 miles an hour. It would swat me like a bug, like a chainmail glove hitting a bug. Some blasts explode in the atmosphere. And by exploding in the atmosphere, they create shock waves. Shock waves, a plane moving faster than the speed of sound leaves a shock wave. We call it a sonic boom. It might rattle your dishes. But a shock wave left by one of these flattens your house. It's a whole other scale. But what happens if it survives the atmosphere? Well, if it impacts Earth's crust, it'll make a crater, as we know. But if it's a big enough crater, it'll thrust the dirt into the upper atmosphere, into the stratosphere. It'll wrap around Earth. It'll cloak Earth with a darkened sky, preventing sunlight from reaching the base of the food chain. And so even if you were not there at ground zero of the impact, where you'd then be vaporized instantly, if you're living on the other side of the world, this stuff affects you because it completely changes your climate. Got a table here just to get a sense of how often these bad things happen. We get certain encounters with these stones once a month, once a year, once a decade, once a century, and the rarer is the impact, the bigger the impact is. And so I put this up just so you know, but every 100 million years, let's look at the bottom number there, every 100 million years, an asteroid 10 kilometers in diameter, has an energy of 100 million megatons of TNT. How many A-bombs is that equal to? 5 billion A-bombs. Can you even imagine that? You can't even imagine that. That's what took out the dinosaurs. That's bad. That's bad. How about once a century? Let's look at that. Come up halfway in the table. Once a century, an asteroid about 30 meters in diameter has an impact of 2 megatons of TNT, equivalent to about 100 A-bombs. Once a century. Once a century. Has that happened? How do we do that? Well, there's a couple of famous impacts that we can refer to. One of them is Tunguska, Siberia. Tunguska, Siberia, 1908. What happened there? 1,000 square miles of forest was felled. "100 square miles of vegetation was vaporized, but there was no crater. What did we learn about it? We studied the event using modern computing. We found a stony meteorite, 60 meters across. 60 meters. Here we have one 30 meters. Same ballpark. It came in, it never survived Earth's atmosphere. It exploded in midair. The energy's got to go somewhere. There's a blast wave, a shock wave, there's a radiant heat, and that destroyed the forests. Get that every 100 years. If that happened over a city, that's the end of the city. Another famous impact, of course, was the KT boundary. All the numbers square with that. That energy, how much impact energy the object had that made that crater, is the right amount of energy that it would take to take out all the life forms, the major life forms on Earth. It all matches. And we get this rate of impacts from looking at the cratering history on the moon. The moon preserves all its craters. There's no weather on the moon, nothing to erode any features that it has. You have craters on top of craters on top of craters. You analyze that, say here's the rate, here's how often big ones come, here's how often small ones come, and you produce a table like this. Now, other planets are at risk as well. We're not alone in this. The moon, as you know, but Mars and Venus and Jupiter. Just a few years ago, 1994, Jupiter got slammed by a comet. Comet Shoemaker-Levy. Those are the co-discoverers. In fact, it was the husband-wife team, Eugene and Carolyn Shoemaker, along with David Levy, patron saint of amateur astronomers. He's got something like 20 comets. I've lost count how many comets he has discovered. The fact that that one was named Shoemaker-Levy 9 meant that comet hunting team, that's the 9th one they found. They found a comet whose trajectory was going to intersect Jupiter itself. It was going to collide with Jupiter. That comet, formerly in one piece, got broken apart into a train of mini comets. Take one comet, break it in two, you got 2 comets by cutting up earthworms. And you calculate the orbit, say, we're going to see a collision of the first rank. Something we've never seen in the era of the telescope. Sure enough, we make the prediction, 1994, July, this whole train of comets slam into Jupiter. Each one of these blobs was enough to have taken out the dinosaurs on Earth. And there was 24 of them running like a train, running like lemmings off the cliff, plunging into Jupiter's atmosphere. Whatever effect it had on Jupiter, you know Jupiter's got no dinosaurs today. That was a bad day on Jupiter. I can tell you this. What are we going to do about it? If we see one headed our way, it's got our name on it. What do you want to do? Well, you can play macho man and say, let's blow the thing out of the sky. But these are big hunks of rock. You'd have to aim right. And by the way, you can't explode. If here's the asteroid, you can't explode something here and expect it to affect your target because there's no air to propagate a blast wave. You need the change in air pressure in order to actually destroy a target. So you actually have to hit it. But there are kinder, gentler ways to accomplish the same thing. One of them is you send little rockets up to it that attach to it, and it gently sort of nudges it out of harm's way. And if you get it early enough in its orbit, you just have to move it by like 1 centimeter per second. And if your collision course was for 200 years from now, that you calculated, and you move it now, catalog every asteroid bigger than about a kilometer, about a half a mile. Those are the ones that would change Earth's ecosystem. You want to know about all those. That would change civilization. Smaller than that, it can be really bad, but we'll recover. One half a mile and bigger, it's not clear that we're going to recover from those. Those are the ones we want to track. Interesting political ramification of this, of course, is that if we find an asteroid headed our way, the asteroid becomes the enemy to everyone on Earth. And all those who were formerly enemies of each other must come together to fight the common enemy. And you'd be surprised how quickly you can make friends when you both have an enemy, no matter what your previous relationship was. I will conclude with the following thought. I don't want to be the laughingstock of the galaxy. We are human beings with a brain. We've got a space program. We know how to launch rockets. I don't want to be caught sitting here watching our species go extinct, being the first life form in the galaxy to have the technology and the intelligence to protect ourselves, yet not actually do anything about it. And if we don't do anything about it, we are no better off than the proverbially pea-brained dinosaurs, who, in fact, had no choice.